this lesson well. Learn to work harder on yourself than you do on your job. I have found in my experience that income does not far exceed personal development. Now, sometimes income takes a lucky jump, but sure enough, unless you grow out where it is, it'll usually come back where you are. Life has strange ways. If somebody hands you $1 million, best you become a millionaire quickly, so you get to keep the money. Otherwise, sure enough, it'll disappear. Somebody once said, if you took all the money in the world, divided it up equally among everybody, it would soon all be back in the same pockets. Success is something you attract, not something you pursue. So instead of going after it, you work on yourself. Personal development. Because true happiness is not contained in what you get. Happiness is contained in what you become. Now, if you're excited and you're ready to change, let me give you 3 steps to start life change that can change your life, your personality, your lifestyle, everything can change. Here's the steps. Number 1, find out how things work. To change your life, really, you need ideas. There isn't anything an idea can't change. And Schultz taught me the major problem is lack of an idea, not a problem. At first, I didn't have any money. I said to Mr. Schultz, I don't have any money. He said, that's not a problem. Now, see, up until then, I always thought it was. Right? I was confused. He said, no, the problem is lack of an idea on how to create money and wealth. It isn't lack of money, it's lack of ideas. So if you get the ideas, see, you can change anything. Now, to get ideas, you need a constant study of finding out. If you wish to be successful, study success. If you wish to be happy, study happiness. If you wish to be wealthy, study wealth. Don't leave it to chance. Make it a study. Some people just go through the day with their fingers crossed. See, that won't do it. You've got to study the things that can change your economic, social, spiritual, personal life. Now, Schoff also said, when you find out something that works, put the information in your journal. Don't use your head for a filing cabinet. Put it in your journal so that you can do the next best thing. Repetition, repetition, repetition. Go over it. And if you repeat it, go over it, sure enough, someday, some mysterious day, the idea takes root, starts to grow, and shows up in your bank account, and your dress, and your personality, and your lifestyle. Now, if you're curious, let me give you 3 ways to find out how to change anything. Any life direction, any dimension. Here's 3 ways to find out how to change anything. Number 1 is to read. All of the successful people I know and work with around the world, they're all good readers. Curiosity drives them to read. They gotta know. They just read. Become self-educated. Standard education will get you standard results. And you can check those numbers and see if that's what you want. But if you want to go beyond that, you now have got to become self-educated. One way to learn is from your own experiences. But another way to learn is from other people's experiences. See, one book might save you 5 years if you read it. Did you know there's books on how to be stronger, more decisive, be a speaker, be a leader, have a better effect on other people, develop your personality? Did you know there's books on that? Did you know that hundreds of successful people have written their stories in books and they wrote down how they did it and people don't read it? How would you explain that? Now, you don't have to read half the night, but put this in your notes, 30 minutes a day. 30 minutes a day, read something positive, something challenging, something inspirational, something instructional, at least 30 minutes a day. Become a good reader. Now, that's my opinion. Listen to the other lecturers and listen to me and make up your own mind. Don't be a follower, be a student. Here's the second way to find out how to change your life. And that's to listen. Get around successful people and listen. Now, you can also learn from unsuccessful people. Take notes on both, negative and positive. Find out what poor people read and don't read it. Right? That's good information. Learn from the negative. But now you can also learn from the positive. Get around successful people. Listen to what they say. Listen to how they say it. It's important. Now, here's some of the best advice I've got for the whole evening. Poor people ought to take rich people out to dinner and listen. That's some of the best I got. But you're right. Poor people don't usually take rich people out to dinner. The guy said he's rich, let him buy his own dinner. I'm not coming up with any money. You're lucky to get your own supper, let alone run around trying to find a rich man to feed. And the guy's behind. If a guy's not doing well, one of the first things he ought to do is find a guy that is doing well and offer to buy him his dinner. Spend $50, $60, $80, $100. Go for the full 9 course. If you get a successful person to eat and talk for 2 hours, they're liable to drop ideas in your lap, change your life. Multiply your income by 2, by 3, by 5. But you're right. Poor people don't usually take rich people out to dinner.
चैट जीपीटी सीखना है आ जाओ.
Scientists have sense. Polaris doesn't act as our stellar models predict, and it is surprisingly hard to get basic measurements for it. How can a star be so clearly visible to our eyes, but evasive to our scientific instruments? Sounds pretty ironic. So let's dive into everything we know and don't know about this enigmatic star. I'm Alex McColgan, and you're watching Astrum. Join me today as we unravel Polaris's hidden companions, explore its peculiar behavior, and reveal why this star could reshape our map of the universe. No, really, wait and see. It's a moonless summer night, and you've wandered to your favorite stargazing spot. Looking up, you recognize Ursa Major, which contains the Big Dipper, a constellation of 7 stars in the shape of a ladle. You follow the 2 pointer stars up and up until you hit a noticeably bright star in the sky. This is Polaris. It sits almost exactly above Earth's rotational axis, so while all other stars appear to wheel around the sky, this one stays put. At the North Pole, Polaris appears nearly directly overhead. As you move south, it appears lower and lower in the sky until you reach the southern hemisphere, and it disappears behind the horizon. But while we've relied on Polaris to navigate the world, it turns out that Polaris itself is far more mysterious and far more complicated than anyone once believed. To us down on Earth, Polaris appears as a solitary, unchanging point of light. That is, unless you use a telescope. In 1779, William Herschel did, and he discovered Polaris had a second star, Polaris B, in a wide orbit. 120 years later, in 1899, astronomer William Wallace Campbell noticed Polaris A had variable radial velocity, suggesting it might have another companion star, one not visible through a telescope. In 1929, a spectroscopic study confirmed this, and we only got our first images of the third Polaris star, Polaris AB, in 2006, thanks to the Hubble telescope. These 3 stars are bound together by gravity in a triple star system. The brightest component, Polaris AA, is what we think of as the North Star. It is an evolved yellow supergiant, 5.13 times the mass of our Sun and 46 times wider. If you placed it in our solar system, it would reach over halfway to Mercury. 2.8 billion kilometers away is its close companion, Polaris AB. Together, these 2 stars form a binary system that completes an orbit every 29.6 years. The third star, Polaris B, circles this inner duo every 40,000 years, at a distance of 386 billion kilometers. That's about 24 times further than Voyager 1 is from us after 48 years of travel. Both Polaris B and A are yellow-white dwarf stars, about 500 times fainter than their primary star. Polaris B is 1.39 times the mass of our Sun, while Polaris AB is slightly smaller at 1.26 solar masses. But Polaris's triple star system is the least interesting thing about it. Its primary star, Polaris AA, belongs to a rare class of stars known as Cepheid variables, which, as it turns out, are one of the
Honey, I have to bring work home this weekend again.
The other side comes for the interview, with your old home now receding into that shimmering spherical window. But are wormholes real, or are they just magic disguised as physics and maths? If they are real, how do they work, and where can we find them? For most of human history, we thought space was pretty simple. A big, flat stage where the events of the universe unfold. Even if you take down the set of planets and stars, there's still something left. That empty stage is space, and it exists, unchanging and eternal. Einstein's theory of relativity changed that. It says that space and time make up that stage together, and they aren't the same everywhere. The things on the stage can affect the stage itself, stretching and warping it. If the old stage was like unmoving hardwood, Einstein's stage is more like a waterbed. This kind of elastic space can be bent and maybe even torn and patched together, which could make wormholes possible. Let's see what that would look like in 2D. Our universe is like a big flat sheet. Bent in just the right way, wormholes could connect two very, very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. So, where can we find a wormhole? Presently, only on paper. General relativity says they might be possible, but that doesn't mean they have to exist. General relativity is a mathematical theory. It's a set of equations that have many possible answers, but not all maths describes reality. But they are theoretically possible, and there are different kinds. The first kind of wormholes to be theorized were Einstein-Rosen bridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat, but curved by objects on it. If we compress that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. A one-way barrier forms, the event horizon, which anything can enter, but nothing can escape, trapped forever at the singularity at its core. But maybe there is no singularity here. One possibility is that the other side of the event horizon looks a bit like our universe again, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole. In the parallel universe with backwards time, the mirror black hole is spewing things out a bit like a Big Bang. This is called a white hole. Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite universe, and they crimp shut in the middle. If you go into a black hole, you won't become the stuff coming out of the white hole. You'll only become dead. So, to travel the cosmos in the blink of an eye, humans need a different kind of wormhole, a traversable wormhole. If string theory, or one of its variations, is the correct description of our universe, then we could be lucky and our universe might even have a tangled web of countless wormholes already. Shortly after the Big Bang, quantum fluctuations in the universe at the smallest scales, far, far smaller than an atom, may have created many, many traversable wormholes. Threaded through them are strings, called cosmic strings. In the first billionth of a trillionth of a second after the Big Bang, the ends of these tiny, tiny wormholes were pulled light years apart, scattering them through the universe. If wormholes were made in the early universe, whether with cosmic strings or some other way, they could be all over, just waiting to be discovered. One might even be closer than we realize. From the outside, black holes and wormholes can look very similar, leading some physicists to suggest the supermassive black holes in the center of galaxies are actually wormholes. It will be very hard to go all the way to the center of the Milky Way to find out though, but that's okay.